So now that we have derived what the change in kinetic energy is, our goal here is to interpret. So now let's get to the interpretation. And so there's a fair amount here. So we have to deal with language. We always have to deal with language because I'm going to be combating everyday language, which is imprecise and incorrect. So here we go. The change in kinetic energy is stored work. It's meaningless to speak of kinetic energy by itself. Only changes in kinetic energy are meaningful. So let's imagine that we do positive work. So suppose positive work is done. Then, according to the work energy theorem, I then have that the external work changes the kinetic energy of this object. Now, if I rewrite this expression, I then write that K1 plus the external work then equals K2. Picture-wise, what do I mean by that? One, I could imagine that I have this amount of initial kinetic energy. And now I'm going to do this amount of external work. But this is not my favorite way of writing it. My favorite way of writing it is to stack them right on top of each other. So if I stack them, picture-wise, they both mean the exact same thing. So when I'm looking at these guys, what am I actually seeing? That if these guys are exactly the same, then what I'm going to find here is that the overall kinetic energy at the end has increased. Because there's positive work, we can see that there is an increase. In other words, I'm going from a low energy state to a high energy state. But the only thing that's meaningful is this guy right here. This is meaningful. This and this is meaningless. And that's a hard comprehension. I think that's a really hard comprehension right there. But that's what we mean. The only thing that's meaningful is the change. So that work doesn't disappear, but it goes into stored work in the change in energy. So another thing that we should go after here is that in the language of the work energy theorem, we could then come in and say the following thing. Work can increase, decrease, or not change kinetic energy. So in the language of what we did before, if I have a speeding up object, whatever it is, that tells us that there is an increase in kinetic energy. And if it's an increase, the only way that could be here is that if I do positive work, which also implies a positive change in the kinetic energy. If I have a slowing object, then we typically say that this is a decrease in kinetic energy. That means that the external work is now negative, which then leads to a change in kinetic energy that is also negative. And the third situation is that if I have a constant speed object, then what you're going to see is that there is zero change in kinetic energy, and therefore the external work has to be zero, which then tells us that the change in kinetic energy is zero. And what you're seeing here is that this one becomes important here, and what you're finding here is that you have an increase plus a decrease in work that offset each other. That's what we mean by that. So now let's go and look at these situations here. So what do I mean by an object that is speeding up where there's an increase in kinetic energy? So now let's go to 3. So what we're going to see here is that kinetic energy depends on speed and mass separately. So the first thing that I'll look at is I'm going to look at velocity dependence. Now, physically, what do I mean by velocity dependence with kinetic energy? So physically, what do we mean by velocity dependence? And you already know. Your intuition is really good at your age. So you gotta think about what work you have to do. So if I now start to write this out, we could then say something like this. So the first thing that we should look at is that we could say that it's harder to make a car go faster. And I can also say that it's easier to make a car go slower. So what do I mean by that? I'm going to imagine that we are pushing a car. Okay, so picture-wise, I think we have a picture of a car up here. So let's steal that image right here that we have. So if I'm looking at this situation here, and I'm viewing this, I could come in here and I could imagine that I have this right here. So here's this car right here. And then what I'm going to do is that I'm going to have the exact same car. And let's see if I can sort of separate these guys like this. So they're both starting like this. And so now, what am I going to do here? Well, what we could imagine in this situation is that now, I mean, I don't know how to draw this, but let's imagine here that in this situation, we have a dog chasing after this guy. Well, since the dog is chasing after this guy right here, what we could imagine here is that this guy, the sucker, doesn't want to push so hard, but this one has a more incentive and apply a bigger external force. I really meant to draw this larger. Maybe I can pull this down a little bit more. So now what I'm imagining here is he has incentive to apply a greater external force here. So if I need to make the car go faster, I got to do more work. And that's kind of what I mean by the language here. So the language says, if I want to go faster, maybe I should have done this large here. What am I going to have to do? You're going to have to, you need a larger work. And that larger work, instead of saying larger work, because we're talking about motion, this is going to be a higher change in kinetic energy. But if you're not trying to go as fast, or then you don't have a need to, then this is going to be a smaller work. And as a consequence, you're going to have a lower change in kinetic energy. So now if I look at this picture here, I could then come and I can look at it and I could just say, yep, here we go. And then if I paste this guy in again, we'll assume here that they are now moving the same distance here. But clearly, this one continues to apply a larger force. As a consequence, this change in velocity is going to be bigger than V1, but this guy is going to be even higher, right? And what we're going to assume here is that they're traveling the same distance from here to here. That's what kinetic energy means. It physically means exactly what you're seeing. You knew this beforehand. So then I start to draw my bar diagrams. So what does my bar diagram say? Well, this one starts off at this kinetic energy. This one starts off at this kinetic energy right here, right? They both start off with the same. And then what's going to happen? We do different amount of work. This one only does a small amount of work. This one, because it applies a larger force, is going to do more external work. So as a consequence, what happens? I get this amount of final kinetic energy, and then this one has a higher kinetic energy, which I'll call prime. So when I start to look at this thing, why is it that the car had a higher change in kinetic energy? It's because we have to look at the stored work. This one did more work, so therefore it had a higher change in kinetic energy. This one did less work, so it had a smaller change in kinetic energy. Only this and that is meaningful. So then if I look at this thing mathematically, in the language of the work energy theorem, we could then just write it down. So in the language of the work energy theorem, it reads like this. It says one of them only did a little bit of external work. And the reason why it only did a little bit of external work, because it only had a smaller external force. The other one did a larger external force because it applied a bigger or larger external force on the car. Because the work was small, I only had a little bit of change kinetic energy. Because the work was large, I had a big change in kinetic energy. So what did I actually see here? I saw here that I went from this guy, I went from a low kinetic, a low speed to a higher speed. But this one went to a much higher speed than what it originally started from. And we could see here that the cause of a higher change in kinetic energy was dependent on speed. And that's what that bar diagram is showing us. This car had a bigger change in kinetic energy because you put more work into this system. We can play the same game again. We just did our, by the way, I should probably, just to make sure that I'm saying this, completely, I could say here is that this is, how do I write this? This was easier to do. This was harder to do. And because it was easier to do, you had a lower change in kinetic energy. And then this gave you a higher change in kinetic energy. That's what the work energy theorem is telling us. It's telling us exactly this here.